Hi, in the last video we've dealt with open economy national income model. But I told you that now that we've done microeconomic model and macroeconomic model, we're going to try something in between, and this is going to be Leontief Input-Output Model. Look, this is going to be a sectoral model. So we are imagining that we have economy divided into sectors that produce different goods. From sector 1 to sector N. Okay, in reality, we actually do this very often in practice in such a way that generally economy is divided into different categories. Then each of these categories is divided into further smaller categories. However, because our model is going to be theoretical, we prefer to think about those categories simply as separate goods. Because remember, technically speaking, even though it would be very, very hard to do, we could divide economy into production of different goods. And this is the case we're going to do here. And every input-output analysis, sectoral analysis, starts with input coefficient matrix. And input coefficient matrix is what you see over here. So, look, this matrix is, of course, of dimension n by n, because we are assuming we have n different goods, and each row corresponds to a separate input, and each column to a separate output. And look, why have we organized this matrix in such a way? Like, if you produce something, you need to have materials to do it. So, actually, you can think about any of the goods that we've got as a possible inputs, so possible materials for production of a different good. And this is exactly what we have inside the input coefficient matrix. Okay, so let's start very simply. What is Aij? Aij, as you see over here, will describe some element out of this matrix. But of course, what does it exactly mean? Aij generally tells you how many cents worth of input I is required or is used. This is Q. Required to produce $1 worth of good or output J. Okay, what does it mean? Look, I know that this is probably not how you imagine the interpretation of it, but we make the interpretation in terms of money. Let's assume that all final goods, and so each of these goods have a price, right? But we are not interested in exact price. However, we can normalize everything to 1. So, what does it mean? Is that now, with each of the elements inside that input coefficient matrix is telling you how many cents worth of an input I, so the ones that we've got here, is required to produce $1 worth of output J. So those outputs that we've got over here. Okay, once we do a couple of examples, I think you're going to get it quite well. Okay, look, let's start with A12. Look, let's just say that A12 is 0.3. Okay, what does it mean? It means that in order to produce $1 worth of good 2, right, you need to use 30 cents of worth of good 1. 30 cents worth of good 1. Okay, now if we would have, for example, A23 equal to 0.2, this would mean that in order to produce $1 worth of good 3, we need to use 20 cents worth of good 2. Okay, but let's just say that now we've got A31 and is equal to 0. What does this mean? Well, this means that if I want to produce $1 worth of good 1, I will not use any unit of good 0. Does it make sense? Of course. If you have a company that produces cars and teddy bears, you can imagine that in order to produce teddy bears, you might need a car, right? This car might be needed probably for delivery, right? And it doesn't need to have a very big impact on the total cost of production of a teddy bear, but it's still in there. However, it doesn't need to work in the opposite direction. You don't need to have a teddy bear to produce a car. And this would be a situation like this. So, what else can we have here? What about A11? Let's just say that this is the case. A11 equal to 0.1. It tells us that in order to produce $1 worth of good 1, we need to use in the production process 10 cents worth of good 1. This might seem counterintuitive. How will we use the same good? Right? Think about a good as steel. In order to produce steel, you already need to have machinery that is built out of steel. And this is the case that we will have on the principal diagonal. On the principal diagonal, we basically have the information of how much of its own production a given sector or even good uses uses in a production process. Okay, so we've got those cases. How about case that we've got A32 equals to 1.1. Okay, what would this result mean? This result would mean that in order to produce $1 worth of good 2, we need to use $1.10 of good 3. Does this result make sense? Technically speaking, it can happen, but is it profitable to produce to produce goods, good 2, if you need to, if in order to produce $1 worth of good 2, you need to use $1.10 of good 3? No. So look, in this case, we cannot accept values being higher than 1 simply because it would mean that the production is not profitable. So it wouldn't be, this good wouldn't be produced because it would cost more to produce this good than you would be able to get for selling it. So in this case we see that clearly this case is not permitted. Okay, now what we see over here in this input coefficient matrix are intermediate inputs. What does it mean, intermediate? You take something that somebody already produced and you use it to produce something different. Right. But this should, knowing that and thinking about this example, should tell us a little bit more about the coefficients themselves. So we know how to interpret them. We know what interpretation can we give on 0. But again, we already noticed that A, I, J, one single coefficient should not be higher than 1. Actually, it should be lower than 1 because otherwise it would be pointless to produce a good on which we cannot actually make money, we would be just losing money. But look, if for now we only accounted for intermediate input. So we are simply thinking about things that other people produced, and we are reusing them to produce something different. But this is not the end of the story, right? We need to also have primary inputs. Primary inputs, the best example is of course labor. Why labor? Well, look, without labor, you will not be able to produce anything. You might have as much as you want of any of the inputs, but without somebody actually doing the production, you will not be able to do. And this actually should give us one more hint about the structure of the input coefficient matrix. Because look, what we get from each line over here. If I'm gonna, for example, take take column first, how can I sum everything? Well, of course, I'm using a sum symbol. In this case, I will have I1, and of course, with I equals 1 and n equal to capital N, right? So we are going from 1 to n. Okay, and look, by the same token, if I would summarize this column, I would just have AI2, then A3, and the last one would be the sum AI. Okay, so now look, let's think about what each of these columns are telling us. Well, each of these columns are simply summarizing, like in each of these columns, we've got elements, those coefficients. If we sum them up, what we get is how much of each of these inputs we need to use to produce $1 worth of 1, 2, 3 until n in total. So look, if, let's just say, this sum is equal to 0.7, what does it mean? It means that in order to produce $1 worth of good one, we need to use 70 cents worth of intermediate inputs. Look, some of those coefficients might be 0, some of those might be big, some of those might be small, but in total we need to spend 70 cents on intermediate inputs in order to produce this good. Okay, now if this column would, if sum of this column would be 0.6, we would have similar interpretation, right? We would have that in order to produce $1 worth of good 2, we need to spend 60 cents on intermediate inputs. All. Okay, and how about if this would be equal to 1.2? That would mean that in order to produce $1 worth of good n, we need to spend $1.20 on intermediate inputs. Again, can this happen? Well, nobody would produce this good because on intermediate inputs you already spend more than you can get. So again, this case cannot happen. And remember one more thing, we still haven't paid our workers. So everything else that we've got over here must go to the primary input. And this brings us to one additional requirement that we should impose that is going to actually outbid this one. Not any of the coefficients inside the input-output matrix cannot exceed 1, but actually the sum of the coefficients over for any column. So if we summarize over any column, for, of course, for j equal to 1, 2, right until n, the sum of each column must be smaller than 1. Okay, I hope at this moment it makes perfect sense why this relationship needs to hold. Because if it doesn't, it means that producing a given good is not going to be profitable. Okay, but look, if this holds, then we know that some amount of money is left after we pay off intermediate inputs. How can we calculate it? Look, again, we can use this expression. So if I'm going to sum up any column, right, like here, and I'm going to take this sum and I'm subtract it from 1, so $1 worth, right, for some given column j, I'm gonna get value of primary input. Let's say that in our examples, primary input is gonna be labor. primary input used to produce $1 worth of good or output chain. Okay, and look, I think this is all the basic information you need to know on input-output matrices, so on input coefficient matrix. In the link to this, in the description of the video, I'm going to actually provide you a link to the database where you can actually see the real live input coefficient matrices. Actually, not only calculated for different sectors of the economy, but also taking into consideration trade in inputs between countries. So it's actually rather big and complex, but you can always just look at one country. Okay, so now that we know how it works, maybe we can use it to find level of production of a given good in a given economy. And actually, this is, as it turns out, this is, once we got this matrix of coefficients, using very simple tricks, we can get the solution right away. Oh, maybe not right away, but you'll see what I'm getting. Okay, so, look. Now, let's figure out for what are we going to spend. Let's denote that x1 is the level of production of good 1, right? Nothing that complex, right? How is this good located in the economy between different sectors? Well, we see that good x1 is used as an input in the production of good 1. So good 1 is used as an input in the production of good 1. How much of it we use it? We use it A11 times x1. But look, we also use good 1 to produce good 2, right? How much we're going to use it? We're going to use A12 times how much has been produced of good 2. I hope you can see where I'm going with this, right? So the total production depends on how much we are producing of the same good, but also how much we produce of the second good, and how much we produce the third good, and how much we produce of the good n. So, of course, we need to have the coefficient, but look, if we produce more of good n, if some people produce more of good n, it means that that entrepreneur that produces good 1 needs to produce more of it to satisfy the demand and requirements from sector n. Oh. Yeah. But this is not it. Look, good 1, right, can also be sold as a final product. And this final product, this demand for the final product, let's denote D1. So this is final demand for good 1. Okay, and look, now we can do exactly the same exercise for good 2. When we produce good 2, part of it goes to the production of good 1. the more we produce a good one, the more is required. And of course, it's given by the technical coefficient from the input coefficient matrix. The more we require of x2. And the same. The more we produce of x2, the more we need of x2. The more we produce of good 2, the more we need of good 2 in order to produce it itself. Of course, those coefficients sometimes can be zeros. And it goes on like this until good n plus final demand. And look, we could write the same type of equation for every case here, right until the good. And we arrive at good n. So we've got a n1 x1 plus a n 2 x2 plus a n xn plus final demand for good n. Okay, now as always when we have problems of simultaneous equations, we will resort to matrix algebra. But before, let's organize variables the way we like it. The way we like it is to have everything endogenous on the left-hand side, everything exogenous on the right-hand side. However, of course, okay, so let's think about what is endogenous and exogenous here. Look, input and output coefficient, well, so input coefficient matrix gives us those coefficients. What do those coefficients depend on? Well, they depend on the technology of production. So, technically speaking, we cannot just take, we cannot calculate them out of the model. The only thing we can do is to take them as a given, because given production process requires some specific inputs, so those are given to us definitely exogenously. But of course those are our parameters, right? Coefficients that lay next to levels of production, right? And levels of production are something we can calculate inside the model. And then finally, what about final demands? Well, final demands we could include in the model, but we're not gonna do because it would just make things a little bit more too complicated without bringing any value to the model. However, we can see that those are going to be taken as given. So we're going to say that final demands, in our case, are given exogenously. So what we can do right away, after what we said, is to put all the expressions with x's on the left-hand side and all the expressions with d, just leave them where they are. And let's see what is happening. Okay, so look, I'm going to first subtract a1 x1, right? On the from x1. So I'm going to get that this is 1 minus a1 1 x1, right? Then I'm going to subtract a12 x2, so we're going to have minus a12 x2, and then we will have those, each next expression will be subtracted, so we would have negative a13 x3 until negative a1n xn, which is equal to d1. Okay. And now we do exactly the same thing for the second equation. So we subtract all the expressions with x's from x2. So first we subtract a21 x1. So we got negative a21 x1. And then we subtract a22 x2. So we get plus 1 minus a2 to x2. Right? And we go on like this until we get a negative a to n x n equals to d2. Okay, and we would repeat this many times until we would arrive at the last equation, where we do exactly the same thing. First, we subtract a n1 x1, then we subtract a n2 x2, until we subtract the last expression. So over here we've got plus a 1 minus a n n x n, and this is equal to d n. Okay, so look, what we see over here is something that we can easily put into matrix notation. Okay, so we're going to have matrix of coefficients, right? And what we're going to have in it. Look, okay, let's start here. Here we will have variables x1, x2, x3 until xn, right? They denote level of production of good 1, level of production of good 2, until level of production of good n. And what do we put inside here? First coefficient will be 1 minus a1, 1, then a1, 2, until a1n. Then we're gonna, I'm sorry, of course, those with minus. Negative a2, 1, 1 minus a2, 2, minus a2n. And we go on like this until the last equation where we got negative a n 1, negative a n 2, until 1 minus a n n. And of course this is equal to d1, d2, until dn, so vector of final demands. So look, what have we got over here? We've taken this system of simultaneous equations and we've written it in matrix notation. However, let's notice one very simple thing about this matrix. If I denote input coefficient matrix as A, what is the relationship between input coefficient matrix and the matrix that we've got? Okay, let's look at it and think about it for a second. Look, first of all, let's forget about primary diagonal. Everything else is exactly the same, but with minuses, right? Nothing's not that hard to spot. However, what do we have on the principal diagonal? We've got also the same elements with minuses, however, in front of them there is always 1. What could we do with matrix A to get matrix like this? Well, if you paid attention in matrix algebra, you know that we could get this if we took identity matrix. Identity matrix, so matrix that has 1s on principal diagonal and 0s everywhere else, right? It just needs to be big enough. Well, it needs to be the size n, right? So they are comfortable for subtraction. And then you take this identity matrix and you subtract from it input coefficient matrix. Here is what we have. Now, we multiply it by endogenous vector of levels of production, and it is equal to a vector D. This is final demands vector. And what you see over here, so this matrix that we've got here, I minus A, so I minus input coefficient matrix, is simply called Leontief matrix. Okay, and now look, if we have everything in this form, it is relatively easy for us to actually find values in the vector of level of production. How would we do it? Look, all we need to do is to solve this equation. So I need to just take this equation, I need to pre-multiply by inverted Leontief matrix, right? So I'm getting that this is I minus A to the power negative 1 times I minus A times X equals I minus A to the power negative 1 D, so inverted A. Those two, of course, turn into identity matrix. But identity matrix times X is just X, so at the very end, what we're getting here is that vector of solutions which contains levels of production in each sector is given as inverted matrix, inverted Leontief matrix multiplied by vector of final demands D. Okay, so now we've got the general knowledge on how a Leontief model works. However, the best way to learn it is by practicing. So, in the next video, we're going to do an example that will show us how to deal with this, how to solve this issue, and we'll introduce one more interesting tool that can help us with this, which is Hawkins-Simon condition. Okay, so thank you for your attention and see you in the next video.